Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone. It's a pleasure to introduce Satish Narayana Sami from University of California at San Diego. Satish is finishing up his PhD. He'll be graduating this June, I think. He's a student of Brad Calder's, who is with the Windows Live group right now. Satish has done very interesting work in hardware support for debugging, especially for multi-threaded applications. And he's continuing that work currently. He has also implemented some of the hardware techniques he developed in a software dynamic optimizer at the Center for Software Excellence when he interned there last summer. And he's also done some work on patching processor design bugs, hardware bugs in the field. I don't know if he is going to talk about that today, maybe a little bit. But
Great.
Here's Satish.
Thank you, Onur. So as you can see, many of you were wondering what process have to do with time traveling. The kind of time travel I'm talking about here is not your science fiction time travel, but it's a feature that would allow programmers to travel back in programs execution time, so which I'll show is very useful for understanding software failures. I'll spend a lot of time talking about how processors can make this feature a reality for programmers. And I'll also spend a little bit of time talking about the two software tools that I built by leveraging this feature to replay a program's execution. So before I get into the details, let's look at the current complexity in software systems. If you take modern operating systems, for example, we all know that Windows, it takes a staggering 50 million lines of code to develop an operating system today. And you can guess how many bugs such complex software systems are bound to contain. And future is even scarier because processor industry have literally stopped working on improving the single-threaded performance. Instead, they're going to give us, almost. Instead, they're going to give us lots and lots of cores. And the key challenge for us today, for a software industry like Microsoft, is parallelize this 50 million lines of code to take advantage of the many cores that we'll get in future. And as you all know, it is very difficult to write parallel programs, and the proportion of non-deterministic bugs are going to go up. So I believe the current challenge for us before today is to make it easier to write parallel programs. And I think it will be very difficult, or I don't think we'll be in a situation where we can say that a software is completely free of bugs. So if the software does fail, we at least need a mechanism that can let us understand why it failed. And we can go for software solutions to solve these problems, but one of the features that I'm going to talk today is going to have a high performance overhead, and this is true for most software solutions. So the solution that I'm going to focus on today is how processors can support solving some of the issues that I talked about. In particular, I'm going to talk about how processors can let us understand software failures. So let's look at the current solution that we have today. So the customer executes a program, encounters a problem. Now then he gets a window like this, which asks him or her whether he wants to report the problem to the developer. In this case, it's Microsoft. Now what it's going to do is it's going to communicate the final state of the system to the developer. Now it's very difficult to understand the source of the bug by just looking at the final system state, because it could be because of non-deterministic bugs, etc. Let me give you an example to illustrate my point. Let's say you have a program's execution time, as I'm showing here. Let's say you have a dangling pointer which you dereference, which is of course an invalid dereference, and as a result the program crashed. Now in order to understand this problem, I can look at the instruction that caused the failure. That will give you some idea about where the problem is. However, it's not going to give us a complete picture of what went wrong that led to this crash. I can look at the stack trace, for example, but then I might have return from a lot of functions that I executed earlier. So that will not give a complete picture either. What I really need is an ability to travel back in time and understand that, okay, sometime in the past, I freed a pointer, and that memory location is what I'm trying to access now. and perhaps even go further back in time and see how the two pointers are related, and go even further back and see the location where I actually allocated the piece of memory. So this could span millions of instructions, and we need an ability to replay a program's execution to understand these things. So as I said, what we really need is an ability to record a program's execution at runtime, probably at the production site, so that when the program does crash, we can communicate the crash dump. In this case, I call it a temporal crash dump. And using this information, the developer should be able to replay the last few seconds that preceded the crash. Now, once you have this ability to record a program's execution, in which case you will be recording the software failure, and be able to replay it, you can build a lot of analysis tools to aid debugging. For example, you can enhance your debugger, let's say GDB debugger, with time traveling capabilities. Now, this is a good situation because if your problem was due to a non-deterministic bug, the underlying replayer is going to make sure you're going to deterministically replay the problem. So you can deterministically reproduce your non-deterministic bugs. Also, you can support features such as backstepping. So you don't if you miss your breakpoints or watch points, you don't have to go all the way to the beginning of a program's execution. Instead, you can just say step back one instruction. And also, I can build a lot of dynamic analysis tools to examine a program's execution. For example, I can build a tool that can automatically analyze memory leaks, for example. I can build a tool that analyzes the data races, or I can do even performance analysis. Now, we were able to do this dynamic analysis over a program's execution, but the key difference with this infrastructure is that it's all done offline, because it's done while replaying, it's not done at runtime. So suddenly the performance overhead of a dynamic analysis scheme is not a big issue anymore. Now, not only that, I can have a dynamic analysis scheme that can go and automatically find these interesting points of events and then give that as a feedback to the time travel debugger. Now, the user can ask the debugger to take him to a point in program's execution. For example, take me to the point where I freed this particular pointer. So instead of setting breakpoints and watch points and trying to reach the point in program execution manually, now that job is left to the debugger to do it. So in this talk, I'm going to primarily focus on providing architecture support for enabling this recording feature. And then I'm going to talk about a couple of dynamic analysis tools that I built that are based on this ability to replay a program. So as I said, I'm going to talk about recording a program's execution using architecture support. So first I'm going to focus on just single-threaded applications for simplicity. And then I will extend that approach to record a multi-threaded program's execution. And then I will talk about the two the dynamic analysis tools. One can automatically find the data race bugs, and the other is useful for building architectural simulators to analyze performance. And finally, I will conclude with some of my other contributions and some of my future plans. So before I get into the details of how to record a program's execution, let's take a look at the requirements for a particular recorder. Obviously, you should be able to replay every single instruction to give you a full picture of what went wrong. Also, it should be able to replay across different forms of non-determinisms. For example, you should be able to replay across system interactions, I/O, DMA. You should be able to replay across multi-threaded interactions as well. The recording should be efficient, especially if you're thinking of incorporating this feature at the production side. Also, the log size should be manageable. And finally, the mechanism that you are going to devise should be portable. Especially when I'm thinking of incorporating this feature in the processor, I want this feature to work across all different operating systems and different system configurations. Also, the information that I'm going to record should be replayable in any system environment. So if I collect a log in Windows XP, I should be able to replay in Windows Vista, for example. Now, there is a solution to record programs execution. Yeah.
Quick question about your portability. Do you assume that when you do the replay, you're on the same processor model? Do you assume that when you replay, when you're talking about portability, you say you mentioned changing the operating system environment. Are you going to require that we have the same processor model so that you can make assumptions about the processors where it has determinism?
I will get into the details in future, but the quick answer to that question is It's dependent on the ISA model, but it's independent of the operating system that's above the processor.
Well, it seems to be also dependent on something finer grained than just the architecture. It seems like you also will be.
We also assume sequentially consistent model. So for multiprocess, we assume sequentially consistent model, and it's dependent on ISA.
Okay, so it really is only at ISA instruction.
Right. It will become clear in the future. Yep.
If you have to do it on a production chip, then getting 1% extra out of Intel is about as easy as pulling teeth. Now, there are these in-circuit emulators that can cost a lot of money. And quite a while back, one of them had 1,000 instruction history window, and I was very happy to get that much.
Right. Thank you.
Now, you want a few million, so a
right.
few billion, which is going to be interesting.
Right. Thank you. So let's look at the solution that some folks at Wisconsin proposed. So this is the only other solution that was proposed to be incorporated in the processor. So the solution they proposed was, well, if you want to record a program's execution from a point, let's take a checkpoint of the memory and the register state. Now there are different efficient ways to do it, but at high level, this was their goal. After you take a checkpoint of the application state consisting of the memory and the register state, one second. Okay, I'll answer take your question.
Yes, I'm sorry to interrupt, but I just realized I had a question. So are you talking about checkpointing a particular application or checking about everything that's happening in the processor? So like you'll capture like context switches, the OS, the interrupts, everything?
Right, that's my next point.
That's what you're getting to. Okay,
right.
What you're getting to.
Right. So you take the checkpoint of your memory state and the architectural context state, like for example, architecture registers, program counter values, etc. So that's the checkpoint I'm talking about there. So once you take the checkpoint, I should be able to replay a program's execution or the full system, right? To do that, you have to capture all forms of non-deterministic input that can affect the execution. So the non-deterministic input can be from multiple different sources. For example, your interrupts, your input that you read from disk network can affect your execution. Your direct memory access can affect your execution. Even the application can read the process clock, which is non-deterministic. So there are all these different forms of non-determinism, and their approach was to explicitly identify these sources of non-determinism and then record it using a buffer, using multiple buffers, in fact. So as you can see, this approach is very complex. It's complex to implement because you're asked to explicitly identify different forms of non-determinism and record each of these sources of non-determinism. Also, it's tied to a particular operating system because the interrupts in system calls are characteristic of a given operating system. So it will be dependent on a system. And the log that you're going to collect is also going to be tied to that operating system because you have to replay the exact sequence of events in the exact way in order to reproduce the problem. You have a question?
When you say tied to the operating system, is your concern that when it's time to replay the next non-deterministic event that represents the operating system having interrupted the process,
right.
You won't have the operating system there to tell you what the data that goes with that event is?
Well, you have to emulate that event, right? So if you have an interrupt, you should have a system. It could be an emulator, system emulator, but that's complex to implement, right?
I mean, it seems like no matter what you do, you either are going to record what the operating system did precisely,
which you're going to do, plus while you're replaying, you have to replay that event exactly the same way.
But I mean, the point is, if you're recording exactly what the operating system event did to the processor's memory state and processor state, then it doesn't matter if you don't have the same operating system because you're not actually using the operating system to replay that information.
Well, so let's say if you have a system call and I recorded the input parameters for that particular system call and the values that were returned by the system call. So now this system call is dependent, it varies between different operating systems, right? So when I have to, when I'm thinking of replaying the full system, which would also involve executing the system code itself, which would involve executing the interrupt service routines, that is going to be a characteristic of the operating system that you're emulating.
Sure.
Right. So the complexity here is due to the fact that you're trying to record and replay the full system. So I will clarify how this can be simplified in a moment.
Okay.
So our goal was, well, let's not worry about recording the full system and replaying the full system. Instead, let's just focus on recording a particular application. So if you look at just recording in a particular application and the shared level libraries, the observation that we made was, well, you don't have to record different events at the system level, in which case you have to monitor the interrupts and DMAs and all these different things. Instead, we can look at the input to the program at the processor level, in which case the source is through the load instructions. So as long as I checkpoint just the architecture register state and the program counter state, and then record the value of every single load instruction that was executed, and then record the value of every single instruction that was executed, then I can deterministically replay the application that I'm recording. All right. So let me give you a sure. Go ahead.
Question just about that insight. Is that your unique insight,
right,
or that has been like
applied
in the
this
area?
Yeah, this is our insight. Like, so BugNet is from now on, it's all going to be our work. Right. So let me illustrate my trick with a example. So let's say you have a program's execution time and you want to record your program's execution from a point. So you would take a checkpoint. Now in this case it would consist of the program counter and the architecture register state. After that I will go and record the values of all the load instructions and the load values. Now this is sufficient for deterministically replaying the application, because if you have instructions like, let's say, addition, for example, it's going to read values from the registers, and you have captured the values in registers because you took the checkpoint. And if you can replay that instruction, you're going to update the registers. So for future instructions, you're going to be able to reproduce the architecture register state. Also, you'll be able to reproduce the memory state because you have recorded the values of all the load instructions. So note that when you take a checkpoint, you don't even have to worry about taking the checkpoint of the memory state, because the values of the load instructions that you're going to record are sufficient. Note that also you don't even have to record the values of the addresses of the load instructions, because even the addresses are computed by reading values from the registers. Now if you have this approach, how do I replay it? Well, you can just take any instruction emulator, for example Box, or even instrumentation tool like Pin, and then you can start off by setting the simulated architecture register state, which you would have recorded during your recording phase. And then I can execute the instruction to which the program counter is pointing, and then I can go ahead and keep doing this and update the register state and the memory state. Whenever I hit a load instruction, I know how to feed the value of the load instruction. Now this is dependent on the ISA, but it's completely independent of the system, because here I'm not trying to reproduce the system events.
What is ISA?
Instruction set architecture. It's like x86 is an ISA, Itanium is an ISA. Yep.
What do you do on Intel,
IS64, sorry.
where the flag settings for half the instructions are undefined because each stepping does a different thing?
Can you repeat the question again?
On Intel, if you ask what an instruction does to the flags, it usually says undefined. Basically, different versions did different things.
So here I'm talking about instructions that are that application normally uses. The kind of non-deterministic instructions that you're referring to, one good example of that is read timestamp, for example.
I'm talking about add, subtract, multiply, divide.
Okay. So the ISA is not defined?
Take a look.
Okay, I will. So I talked to some of the guys at Intel, and it's probably a bug rather than an actual feature that you would like to have, right? Is that right? Or
yeah, but it's a bug that exists in real.
right. Anyway, so here I'm assuming a clean x86 interface.
So you have to keep track of, you say load values and instructions. By instructions you mean the instruction address, the actual instruction stream?
So here I'm referring to the value of the instruction, the machine code, not the address of the instruction, because address you'll be able to deterministically reproduce.
Okay. But you can't deterministically reproduce the
No, because
contents.
you can't tell if the operating system remapped the memory page when you want to.
Right, or somebody else wrote into it.
Right. So I'm going to get to how to
So you're
optimize.
just recording all the bits that go into the processor, basically.
Right.
The instruction that the
Right.
is going
Right.
to. Okay.
So I'm essentially recording everything that you read from the memory, whether it's a data space or the instruction space, doesn't matter.
Presumably you also have to read things like, if I look at the Pentium cycle counters, it's not coming.
Right. So that's one exception that I was actually talking about while answering this question. So if you're reading the machine state, you have to record that as well. So here afterwards, I'm just going to refer to loading values as load values instead of distinguishing between instructions and data. So obviously recording every single value that you load from memory is going to be very expensive. It's going to be expensive in terms of log sizes. So instead, I made this observation that you need to record a value that you're loading only if the load is accessing the memory location for the first time after you took the checkpoint. So for example, if I have a load to location A, reads a value, and then I have another load to different location B, I read another value. But then when I read from the same location that I had previously logged, I don't have to record it again for obvious reasons, because during replay, I will know the value in location, what location A is.
Unless you're multi-threaded, or there's a DMA into there, or...
Yeah.
Right, so I will get to all those problems in the next few slides.
Well, you said you didn't need the load addresses. Now you're trying to detect they're the same.
Those are the values. Well,
Those are the values.
He means he doesn't
Load
need to store,
addresses,
he
he
doesn't
has
need
in
to
the
store the
registers.
addresses.
The addresses are all in your registers.
Right. You're computing from the registers. You add immediate value to the register or whatever.
I mean, you're right. He needs to know the load address to do this computation. He doesn't need to save it in his trays. Different question.
So getting back to your question, like how do you handle the DMAs, interrupts, etc., that's in my next slide, actually, the slide after that. Before getting into that, first of all, I should be able to observe this property while I'm executing a load instruction. So I need to know whether the value that I'm loading from a memory location, whether I have logged earlier or not. So this is a binary decision. So I can associate a bit per cache block, because every time when you execute a load instruction, you're going to access the cache. And I can set this bit when I log it, and then when I read the value again, I will see that the bit is set, so I don't have to log it again. Yep.
You really have to log the whole cache word.
Right. So it depends on which granularity you're tracking that bit. If you're tracking for every bit, of course you don't. That's going to be expensive. So what about store instructions? Well, store instructions, if that is the first memory access to a location, then I don't even have to record the load value that follows it, because I can deterministically replay the store instruction. So in this case, I would know how to execute a store to location B, so I know the value in location B. So when a load follows the store, I don't have to record the value for this load, because I already know how to get the value for location B.
This has the same cache word problem, right? If you store less than the whole cache word.
Sure, that's the same problem. Yeah.
Well, no, but I mean, what are you going to do? If you've got a cache word with the bit already set, there's nothing to do anyway. There's no optimization. If you've got a cache word with the bit not set and you store part of it, do you log the rest of that word? How do you take advantage of this optimization?
Well, so the optimization here is that if you are going to execute a store operation, you're going to set the bit.
When you say cache word, I guess you meant cache word, not cache line. You really mean 32-bit word.
Right.
So you got a bit per 32-bit word.
Right.
Okay. So most of these stores really
Right.
are a whole.
Right. If it's going to be subvert,
Sorry.
then yeah.
I misunderstood what you meant earlier, but.
Yep. So as someone pointed out here, there could be a lot of other system events which could upset this optimization, because, one second, because any of these events in the system could potentially modify the locations. Your question.
That 1 bit per word is already 3% penalty on a performance critical part. And it's worse on Intel.
You can associate those bits in a different tag set and then do all this analysis offline. So let's, do you have a question?
Oh, we're discussing what you're going to say next. Why don't you just say it?
Okay. So as everyone is discussing, interrupts in system calls could be a problem. Now, let's say again we have a program's execution. Let's say you get an interrupt. Now, the trick that I played was, well, before you start executing your interrupt, I'm going to prematurely terminate my checkpoint. Okay? And then after servicing the interrupt, I'm going to start a brand new checkpoint. So what this means is I'm not going to record anything that went wrong during the execution of the interrupt, so I'll not be tracking the system code's execution. So when I come back after servicing the interrupt, since all the log bits associated with the cache line would have been reset, that would automatically force the future access to the location to be logged. So for example, if a system call executed a store to a location, the future load executed by the application would record it. Does it make sense?
Yep.
What about DMAs? Well, let's say you have the same load optimization again. Now let's say you have a concurrent update to this location A. Now in modern processors, before concurrent updates can be made, you have to first get write permission to the block. So this is done using a coherence message. In this case, it's an invalidate message. For the processor, pseudo processor executing the DMA, it has to send an invalidate message to the current owner of the block, invalidate the cache line. So at that point, I would just reset the log bits associated with that cache line. So future, if the program execution again accesses the same block again, since the log bit would have been reset, that would force the value to be logged again. Does it make sense? Yep. Okay. So the architecture support that you would require in order to do these optimizations is the following. You need a bit per cache word in your private caches, and then I need a checkpoint log buffer to buffer the logs that I'm collecting, and then this has to be repeated, continuously returned back to the space that you have allocated in the main memory. And the performance overhead for this, the primary bottleneck there is the bus bandwidth that you're going to use to write your contents back to the memory. So if your application is not memory bandwidth limited, the performance overhead is about 1% for the applications that we analyzed. And the question...
That 1% comes from the occasional memory stall.
Right. So, and also another question is, how much space should I allocate in the main memory to capture the program's execution? So for example, to capture 100 million instructions across different spec applications and different open source programs that we analyzed, we required about 3 megabytes of data. So in summary, to record a program's execution, you just need to record the architecture register state and the values of the load instructions. And this requires a simple extension to the cache and a memory-backed on-chip buffer. And the advantage is that performance overhead is tolerable, and you don't have to worry about the different system events in the processor. And the log size you would require is about 3 megabytes for 100 million instructions. Note that the increase is not linear, because the longer your checkpoint size is going to be, the better your logging optimization, because you're going to save redundant logging. So now that I have convinced you about how to record a single-threaded program's execution, I will move on to recording multi-threaded programs execution.
Can we ask questions about the previous one first?
Sure.
So what is the, I'm guessing by those numbers that the memory bandwidth you're using is something like 30 megabytes a second? Is that?
No, that's tiny.
It's about 128 megabytes per second.
Okay.
I don't quite recollect exact configuration now, but it's around that ballpark.
What memory bandwidths do I expect out of these processors? I mean, I have no idea what I'm comparing that to. I mean, you said this is only an issue if you have a memory-bound application, which some are. So what fraction of the full memory bandwidth is that, of the available memory bandwidth?
So one other way to think about it is the amount of log that you're going to generate is proportional to the cache miss rates. So whatever data that you're going to bring in.
Basically 50%.
Right.
Okay.
So one other question. You have this load and store load optimization where you don't record things in those instances.
Right.
Presumably you have to have some kind of state somewhere that's able to track that, so you know when to apply that optimization.
Right.
Where does that go and how much processing?
Oh, that's associated with this cache line, right? The bit associated with the cache line is what's going to let you do that optimization.
So you only do that optimization over things that are in the same cache line. Oh, okay.
So it's done at the...
If the cache would get flushed out and then reloaded.
Right. Then, so that's why I said it's proportional to the cache miss rates.
Okay.
So did you see any applications? You said about 1% for a bunch of applications. Was that averaged over a bunch? Was some higher than that? Did you see any applications that?
So there was just one application which was around 5%. That was Ocean and Splash benchmarks, which was memory bounded. But for the application,
5, not 50.
No.
Okay.
No. Definitely not more than 5%.
Did you try to run this on something like, say, SQL Server? Just
Nope.
Pick an application that's been known to have bad cache performance in the past. Okay.
What was your baseline memory bandwidth assumptions?
Um,
What was the memory bandwidth in the baseline processor?
So I don't quite recollect it, but it's around 128 megabytes per second.
That's quite low, isn't it?
Yeah, that's really small.
Wait, did you? That seems like the same number you told me when I asked what the bandwidth that the tool, that the log used, not the bandwidth that was available in the processor, which I think was.
Yeah, I was asking the memory bandwidth you're getting from
Oh.
DRAM.
Yeah, like not
The peak
not
throughput
how
you're
much are you using? What's available?
Oh, okay. That's about 1 gigabits per second. So let me get on to recording multi-threaded applications. So let's look at how to record multi-threaded programs. So again, I'm showing multiple threads executing in multiple processors. We can think of a model where you record each individual thread by itself. That is, you would apply BugNet optimization for each thread. So with this model, since I'm recording the values of all the load instructions executed by the application, right, I will be able to deterministically replay the thread corresponding to the processor in which it's recorded. So it looks like I've solved the problem associated with the multi-threaded programs, because now I am able to replay the threads executed by the application. Right, exactly. However, before getting into even that, you have to worry about concurrent updates that could affect your logging optimization, which is exactly same as your scenario that we had for DMAs. Right? So I don't have to explain this once more. However, you have to record the interactions between the threads so as to understand data races and other concurrency issues. So let's take an example. Let's say I detect a dependency in the processor. Excuse me. Now I can detect this dependency by monitoring the coherence messages in the processor. I'm not going to get into the details of how exactly you can detect the dependency, but assume that you are able to detect the dependency. Now the question is, how can I record this dependency? One obvious way to do it is to record the timestamp for the store instruction and record the timestamp for the load instruction. Well, you'll have lots of such dependencies, and recording the timestamp for every single dependency that you're going to see is going to increase your log size. Instead, the mechanism that I proposed was, let's record the timestamp of the current timestamps of the processor nodes. For example, I would record the timestamp of the processor node T1 and record the timestamp of the processor node T2 just before I executed the load instruction. Okay. And I will also associate a label along with this timestamp so that during replay I can take these labels and then match these timestamps and know that there is a barrier or a stratum that separates the executions of the threads. Now this gives you a happens before relationship between all the memory operations that were executed before the stratum from all the memory operations that were executed after the stratum. Yep.
Are you doing this just so that when we replay, the debugger can tell me when each thread was blocked? Like it's not required to actually replay a particular thread all by itself.
So you can replay each thread all by itself, and we are trying to figure out the dependencies between the threads. And my question is, what you should record in order to figure out the dependency.
I'm just making sure that what you're doing here is not something that's required because of the new environment. You're doing something that adds an additional value to the output, which is the ability to stagger the play of the threads in some order that's consistent with the order.
Exactly.
Let me understand what you're really doing here. So every time you have a load that you have to record a value on one processor, you have to capture timestamps from every processor to do that?
Only these certain loads.
Only the dependent nodes, but actually if you have more nodes, you're going to capture the timestamp of all the processor nodes.
Oh, it's all the processors?
Right, and this scales well for the SNU-based systems, but for directory-based systems I have a solution too, but I'll not have time to get through it, but we can discuss it offline.
So how can you tell it's a dependent load? I understand you see it's a load because there's cache validation traffic that has to go there, but there could be a long time from when you see the cache invalidate to when you actually make the load.
The thing is, for you to execute the load operation, you have to get the read permission for that operation. So that's going to send coherence messages to get that permission. Now, it's a different issue what happens when things get outside the cache, like what happens when you evict a cache block, right? So how do I know it?
Right,
so
I'm trying to see how you differentiate loading from an evicted cache block or cold miss from a code.
So note that the more stratum that I'm going to log, the better it's going to be. So whenever I am going to have a fetch a block that is not in anyone else's cache, I can always log a stratum, right? That's going to allow you to infer a happens before relationship.
Sure. It's just a question then of, do you spend all your time writing down timestamps? But okay, I guess you'll tell me that in a minute.
Yep. Well, I'm not sure exactly what your question is, but let me finish this solution and then.
You start to write an awful lot of data now.
Not quite.
You've got to write a timestamp for every processor for every cache miss, right? So your work goes up kind of.
I'm going to get to that.
Dramatically. Okay.
So, for example, if you have another cache miss that for which the dependency spans the stratum that you had previously recorded, then you don't have to record additional information, because in this case, during replay, I can automatically figure out the happens before relationship using the stratum that I had previously logged. Does it make sense?
I just don't understand where you're storing the data to determine if that happened.
So,
I understand why that's sufficient to record, but I don't understand how you can tell that at runtime.
right. So this is done with associating a bit per cache block, so additional bit per cache block. Unfortunately, I'll not have time to go through it because I'm already running it.
I have you right after the talk,
Right.
so we can do it on my whiteboard.
Right.
So the fact that you do it on a cache block basis, there's some false sharing, right?
Right.
So it's not exactly store A. It could be store A and then load
Sure.
C, and you would
Sure.
still
Sure.
record it.
Yeah, false sharing could also lead to unnecessary locks. So if you have a dependent operation that does not span the previously recorded stratum, obviously you have to log another stratum. So the summary of this multi-threaded execution is that using load values and the instructions that you're going to record, you can replay your thread, but in order to infer the dependencies across the threads, you need to log more, and I proposed a stratum solution which is 12x smaller than the previous solution in terms of the log size. And it can also be supported in Snoop-based systems, which was previously not possible because of the reason that you brought out, because you don't have any place in the system where you can track information about who last wrote to a cache block. And it can also be recorded in a directory-based systems without a lot of complications. We can talk about it offline if you're interested. So the final two things that I want to talk about are dynamic analysis tools that we built in order to, one is to find data race bugs, and another is to analyze performance bottlenecks in architectures. This is useful for building architectural simulators. So again, to show you the usage model picture, so I have talked about recording a program's execution, and now I'm going to talk about the two dynamic analysis tools that you can build by replaying a program's execution. So obviously I didn't have any architecture support, so I had to build this in software, and I did this using pin instrumentation tool. So anything that I described, that was all implemented using a pin instrumentation tool. And Microsoft has actually independently developed a similar mechanism, and they call this tool as IDNA. And it's been, I think it's getting used very widely. It's used to fix over 1,000 bugs in Vista. The problem is, of course, this is software implementation, so the runtime overhead is around 15x for computationally intensive programs. And last summer I came here and I worked on building this dynamic and data race analysis tool that leverages the ability to replay a program's execution. And I'm sorry?
That date race is a typo
Sorry about that.
in red. I'm just asking, because if it's not, I was
This
going to ask what that is. No, right above it, it says DATE instead of
Okay, that's data race. Sorry.
Fine. Okay.
So what is the data race? So you have a piece of code which two threads execute, and as long as the operation is done atomically without, so since you're not using locks, there could be a problem that there's no synchronization between the concurrent operations. This is a traditional data race problem, and if the interleaving, if the two operations interleave, then the read can read the incorrect value, giving you an incorrect reference count. So what we really needed here was lock operations to ensure atomicity. Now there could also be another data race here. So there are two possible data races in this piece of code. Now I can go and find these data races and identify the concurrency bugs. That's not a big deal. But the problem is 90% of the true data races that you find in the multi-threaded programs turns out to be false positives. And my goal was to automatically identify whether a data race bug is a harmful bug or it's a benign bug. So it could be, a data race could be benign because of many reasons. So one of the example here shows you that an optimization for a program is figured out by a concurrent thread, and one of the thread executes one of the two square root operations based on what the optimization level is. Now it doesn't matter what the optimization level is, you're still going to produce the same result. So this is an example for a benign data race. Now if you're going to report all the data races to the developer, it's going to be very time consuming on the part of the developer to triage them. So the trick I played to automatically identify whether a data race is harmful or not is the following.
So that 90% number, for what kind of applications?
It was for IE and Vista services. So the trick here is, okay, you take a data race, you take a dynamic instance of a data race. Now there are two memory operations involved in the data race. The simplest thing you can do is try out the replays for two possible orders between those memory operations. So if the two replays corresponding to the two possible orders are going to produce different results, then it's potentially an indicator that the data race is harmful. If the two orderings are going to be exactly the same, produce the values that are same, then it's an indication that it's benign. So for example, if I have the same piece of code, I detect a data race between the read and the write operation. Now I can rearrange the order to be different and then try to replay for this new order that I contrived. Now in this case, the read is going to read a different value and it's going to expose the data race bug. So in this case, I'm able to identify that this is a harmful bug because the net result produced by the replay is going to be different in terms of the live outs from the actual execution that was seen. Yep.
What is a live out exactly?
So live out is the memory state and the architecture register state.
In your optimization example, it's going to take a long time to discover that those are the same.
Right. So it's not completely precise. So there could be false positives, like some of the bugs being incorrectly classified as harmful, even though they are not harmful. So that I will get to that result in a minute. Actually, it's right over here. So when we analyzed about 68 data races in Vista and Explorer, 7 of them were found to be harmful. That is, when you replayed for the two possible orders, they produce different results. And then 39 of them were really benign data races, but only we correctly classified 32 of them. So the 7 of them were because of the reason that you mentioned, which is if the program's execution doesn't converge very fast, then you'll not be in a situation to consume the logs that you had recorded. And even one other limitation is that there could be data races that are benign because the developer intentionally left those data races in the code because in order to get performance, wherever you can guarantee that the code is correct, for example, if you are updating a statistics variable, you're not worried about exact correctness of the code, but instead you are worried about performance. So there you choose to not use logs in order to get correctness. Does it make sense? So those cases will not be correctly classified using the technique I proposed. However,
Those would be your false positives?
Right.
Okay, right.
Is this implemented in TrueScan?
Right.
Right.
This is part of TrueScan, yeah.
Sorry, what's approximate code?
Oh, that's the example that I was talking about, where you have a update to a statistics variable, or you have a model for a cache where you don't worry about which cache line you're replacing. You have a question?
Okay, so at the beginning, I didn't know if you know about IDNA, so I didn't mention it. So actually, your work on IDNA is quite different because IDNA rely on Nirvana, and that can only log the instruction in the user domain, right? Anything happen in the kernel, they cannot.
And that's
log.
exactly what we did too, right?
But you said you did in the processor level, right? So
Right,
anything
so
happen in the processor, including the kernel instructions, you save it.
No.
No.
So we focused on just capturing the user level.
Yeah, only the application level.
Right.
Okay, I see.
Since you're logging since you're doing this based on replaying and then perturbing the order of the replay, it seems like the only case I have in my head for a benign data race is the example you gave me, and it seems like you don't have to diverge very far before you can't replay because you don't actually have the loads that you would need on the on the diverged path.
So I could give you an example where this would work. For example, if you're operating different fields in the same data field, like 32-bit word, it's a different field. Though you'll be detecting the data race at the granularity of the word, then that's a data race.
That's an instance of something you found in the
Right. So the final piece of thing that I'm going to talk about is this performance analysis application. Now, the problem that I'm trying to solve here is the following. So in architecture, we traditionally use application-level architectural simulators, like, for example, Simple Scalar and ASIM. Now, these architecture simulators, they have to functionally execute the program correctly. So what that means is you have to execute the system calls and the interrupts correctly in order to analyze the performance of the sequence of instructions that are executed. Now, the system emulation part is what makes this approach complex, because you have to emulate the system calls and interrupts and so on. Obviously, developing a system emulator is going to be difficult to develop, and it's also going to tie your system to the host operating system and the emulated operating system. And also, typically, DMAs and interrupts are not handled by the system emulators. And as a result, Simple Scalar was pretty much tied to evaluating Linux-based applications for over a decade. So what we really need is an ability to write architecture simulators that can potentially work across different platforms and different applications. So the solution that we did was, well, BugNet is system independent. So you can record a program's execution on a platform and then replay it in any other platform and hook your architecture simulator to the back end of your replayer. So this was a solution that we developed, and it's called Pincel, and it's currently being used at Intel for evaluating Mac OS applications, which they never were able to do it before because of the effort involved. And we also ported Simple Scalar x86 to evaluate applications involving interrupts and DMAs. Now, finally, I'll conclude with some of my other contributions and some of my future plans. Well, the question here is, not only the software has bugs, but also the process that we use in your desktop processors or systems today have a lot of bugs in them. For example, Pentium 4 has 109 bugs, and AMD 64 Optron has about 63 bugs. And these are published in the errata sheets routinely. Now, the question is, we don't have a support in the processor that can transparently patch these bugs, just like how we are able to patch the bugs in software. So how can we patch these errors? Something like a Pentium update, just like how we have a Windows update. So the observation here that we made here is that process design errors are really corner case bugs. What that means is the bug manifests under a very rare circumstance when the stars align. For example, if you take Pentium 4 bug, for example, the page faults in two virtual processors in a hyper-threaded processor should occur exactly at the same cycle for the page fault to be incorrectly handled. Now, we can specify this bug using specific processor events. In this case, I can specify the bug using the two page faults and specifying that those two page faults should occur in the same cycle. And then I can design a field programmable patching hardware and then leave it on when I develop the processor, so that later on when I discover the bug, I can go back and program this hardware unit, which would then monitor for these processor events, correlate those processor events, and detect the error condition. So once you detect an error condition, you can recover by several means. So one of the obvious things that you can use to recover is to roll back to a previous checkpoint and then replay. And while you're replaying, it's very unlikely that the two page faults will again occur at exactly the same clock cycle. So when we analyze some of the errors that was published in, all the errors, in fact, published in AMD 64 errata sheets, we found that 78% of them have the potential to be patched. So we can sort of extend this mechanism to detect and debug and patch automatically the bugs that we have in software. So for example, when the software crashes, we can have an automated root cause analysis, a dynamic analysis technique that can replay a program's execution and understand the key events that led to the crash. For example, the sizes of the buffers that were size of the buffer before the program crashed, for example. And then I can report this root causes to the developer instead of reporting the whole BugNet log, because this is better now, because it's going to solve some of your privacy issues that are associated with reporting the full program's execution. And then I can have a hardware mechanism that I can use to program and monitor for such events, which could potentially detect the bugs online and recover through replay as well. For example, if you want to fix your data race, you can roll back and replay, and the schedule that you're going to get is going to automatically patch the bugs. So in summary, we are at a time where processor industry is starting to look beyond performance. So it's starting to look at additional features to improve security, debugging, etc. And the BugNet architecture is one such feature that can add more value to the processor. And the key insight that we had was, let's focus on the application's execution and not worry about different non-determinism at the system level. And this enabled us to record and replay applications independent of the operating system. And one of the software tools that we built out of PIN is currently being used at Intel as part of its tool chain. And the tool that I developed as part of my internship is getting used here along with TrueScan as part of TrueScan. Yep.
In the hardware patching thing, how do you determine whether something is a soft error or a hard fault?
That's a hard problem, but my goal there was not really to identify the problem itself, the bug itself, but once you find the bug, how do you go about patching it?
But you had a slide that said self-healing, so you have to automatically determine.
Okay, so for that part, yes, you have to do it.
Okay.
Most of the time, the problem is with the software. So isolating the problem is a key challenge, and we do have some solutions to patch the processor bugs. For example, ECC's machine check codes allow you to isolate the hardware bugs from the software bugs. So isolating problems between hardware and software itself is a big research area.
Yeah, actually, but I was asking about soft errors. So these are transient hardware faults.
Right.
Right, so that's yet another class of errors.
Right. So isolating faults, nailing down the root cause itself is a interesting problem.
A similar train of thought. You do this based on signatures. How do you ensure that that signature actually corresponds to the bug and nothing else?
So you can have false positives.
Program. Yeah, if you have false positives, you may be patching something wrong, and you would be.
So the only
impact
that only cost you're going to pay because you did not match the correct bug signature is going to be performance, right? Like as long as you don't have false negatives, you're fine. If you have false positives, the penalty you're going to pay is just performance, and that's going to be rare as long as your signature is going to be specific enough.
Okay, I guess it depends on what you do based on.
Right. So the kind of things that you do are replay, which is benign, right? And probably you can. We also thought of inserting no ops into the instruction stream, which is also benign. So such things are not going to affect correctness, but will affect performance. But then you're going to trigger these things only very rarely.
Okay. So that means the patching mechanism is limited to some certain kinds of bugs.
Oh yeah. We didn't patch all the bugs. Only 78% of 100. Yeah.
And the second question is, have you thought about the security implications of this patchable, programmable hardware?
So I get this question very often, which is we already have in current systems. So that there were some security attacks using the BIOS patches. I don't have a good solution to that problem.
Two small points. One, have you looked at Intel bond-out chips?
I'm sorry?
Have you looked at Intel bond-out chips?
Nope.
They have some context paths on the chips that they don't sell to most customers, but they expose them for debuggers, which means you don't much care for the cost after that.
I see. So
I think that's how Intel ICE in-circuit emulators are made. They have special chips with extra pins, so extra bandwidth you can steal without bothering other people.
Interesting.
And the other is, if the square root were replaced by sine and cosine, you would have a bug. Even with square roots, you should check your rearview mirror.
Sure.
I was just going to ask about the economic benefit. So is there any evidence that these hardware bugs? I mean, you said that there's 89 whatever bugs in these various processors are actually impacting users at the level that they notice that they exist.
So we don't have a quantitative measure on how much these are economically impacting, like what's the economic impact of it. But there are cases where the process industry go out and recall their processors. For example, 2 years ago, AMD recalled its Optron processors, about quite a few thousands of them. So whenever it becomes popular, like FDIV is another example where it cost Intel like $450 million, right? So there's no like scientific study on what the economic impacts are, but once the bug gets popular and the users get aware of it, more and more aware of it, the process industry have to go through the trouble of replacing their processors, recalling and replacing the processors. And having such a mechanism is, and apart from improving the reliability, it's also going to save the pain of going through this replacement cycle. Okay. Thank you.